1 second. Yeah, great. All right. Thank you, everyone, for being there. And thank you, François, for the great introduction. Thanks for inviting me. It's great to have you all here today. I want to talk to you about what happens when you tightly focus in air a millijoule class femtosecond laser. It was quite surprising what happened to us in the first place, and then we investigated a bit further, and it turned out to be a slightly more scary than we thought at the beginning. So I really want to share that with you. So most of you don't know me that much, so I just want to have a quick words about my academic profile, even though François said it already. So yeah, so I did my engineering physics at Polytechnique, then master's at McGill in medical physics, then at INRS and Université Bordeaux for the PhD, and now at University of Waterloo for my postdoctoral studies. So just to give you a bit of context, it started about 10 years ago during a research work done on longitudinal electron acceleration, the topic that Jeff will talk about in his poster. During that experiment, very low levels of radiation were observed during the alignment procedure in ambient air, and only with 100 microjoules of laser pulse energy. And since then, since 2012, there was a recent laser upgrade, now up to 3 millijoules, which made us a bit more cautious about radiation safety. And since the experiment started back on that topic, now the All infrared beamline can deliver 2.8 millijoules. Now it's even more than that. 12 femtosecond and at a wavelength of 1.8 micron, and it runs at a repetition rate of 100 hertz. So just by sending this laser on a tightly focusing optic of this one is an NA of 1. It's a very simple optic that is a 1 inch, less than almost $1,000, so very simple one. It turned out that our Geiger counter measured the high levels of radiation 3.5 meters away from the source. So we stopped it there and wanted to investigate a bit more about what's happening exactly, and because it was a bit surprising and impressive to see that in the first place. So there were many questions to answer. What's the absolute dose rate? So what's the risk level that is associated with it? What's the scaling of those with pulse energy and distance? Now, what is the particle type? Is it just electron, X-rays, or both? If it's electrons, then 3.5 meters in air corresponds to 0.9 MeV already, so that's a lot. If it's X-rays, then there's a substantial amount at 3.5 meters. So in both cases, it was not a good sign. What's their energy? Is it keV or MeV? Where is it coming from? Is it just the parabola? Is it the optics on the table? Is it just the air? What's the divergence? Is it isotropic or not? And then also, most importantly, how is this possible considering the intensity clamping in air? It's very surprising to see that much dose so far away at 3.5 meter. So the thing is that actually I forgot to mention, a Geiger counter is a really bad absolute dosimeter because it works in saturation mode, and also the quantum efficiency is quite low in the low keV region, so it underestimates the real dose that you measure. So we've done an experiment with 2 medical physicists from McGill, my old colleagues, and essentially the setup boils down to 2 optics. It's probably one of the most simple one you'll ever see. 1 mirror and 1 tightly focusing optic, NA of 1, so almost 180 degrees light cone. And then we measure those at an angle with 2 ionization chambers, so one for low and one for high dose rates. We're limited here in angle by the last mirror that blocks the view. And additionally, we also use 2 passive area dosimeters from Health Canada at 2 different distances from the source. And all of this is performed in air. We just send the laser on the optic and measure the dose. Now, a few disclaimers about radiation safety. I want to mention that the personal dosimeter of each person that attended the experiment officially reported no dose because we were cautious in what we were doing, and also that precaution and ALARA principles were applied at all times. So maybe a reminder for some of you, ALARA means as low as reasonably achievable. So in practical terms, it means using radioprotective shielding, such as lead walls, maximizing the distance from the source, and also minimizing the exposure time. So here's the main, the golden graph that I want to show you. Just to put you in context here, I show the dose in milligrays over 8 orders of magnitude, so from 10 to -4 milligrays to 10 to the 4 milligrays, and 4 different distances from the source. And we also did many laser pulse energies for the different colors. And you see 2 sets of points. So the triangles are is the high dose rate ionization chamber, high dose rate dosimeter. And we completed the data set with the other ionization chamber for low dose rate measurements. And so maybe one point that we could put here, one line, the Canadian Nuclear Safety Commission sets a public dose limit of 1 milligray per year for electron and X-rays. And so this is about here. And so here I write, this is a moderate danger region, meaning that in that region you get your annual dose. If you're exposed to the radiation produced by the setup, you get your annual dose within a few hours to a few minutes. And then if you cross that line, but you're below 1 minute, because this is all 1 minute acquisitions, you get your annual dose within a minute. So this is a quite high exposure risk here. The highest point that we measured a max dose rate of 9 grays per minute, and the radiotherapy level starts about here. So usually radiotherapy is below 6 grays per minute. So we were above the threshold of radiotherapy. So it was quite surprising for us to see that we just have one focusing optic and we can generate that much dose. But probably the most practical point that we should look at is this one. So at 1 meter from the source, which is essentially a typical distance from an experimentalist to an optic, at 2.8 millijoules at 1 meter from the source, exposed personnel get their annual dose in 0.8 seconds. And this is not a mistake here with minutes, it's really seconds. So this is definitely of a concern here when people use these kind of optics and align it, and you watch a plasma in air, at the same time they could get irradiated quite a lot and be well beyond their annual dose limit that is set by the CNSC. So this is a radiation safety concern here. Now, if you take the same data without processing and you just replot it another way, so again the dose in milligrays, but now as a function of pulse energy, and for different distances from the source, well, you get those kind of lines. So this is in log-log here, and I fitted power laws, and it turned out that the exponent was between 4 and 6. So we observed a highly nonlinear dose scaling with pulse energy. Of course, this is just within that window, which is quite narrow, and we expect a saturation a bit above here, but nevertheless, it's a really nonlinear, highly nonlinear dose scaling. It was a very strong effect that we observed. If we look at the divergence, so for a fixed radial distance around the source, we get the relative dose as a function of angle around the source. We observed a highly directional emission. So here's the half angle of the cone was below 17 degrees. Here it's 17, but the curve is normalized to 100% at 4 degrees, simply because we couldn't access the 0 degree point due to the last mirror that blocks the view. So I write less than that because it's most certainly below that for sure. And also electrons, they scatter a lot, X-rays also. So if we would have measured closer, it would have been smaller even. Also, just to mention, the two previous graphs that you saw were done for the dose scaling. They were done at 20 degrees. And so you could essentially take the dose, the absolute dose values that you saw there, and multiply them by at least a factor of 2, because this is about 40% of the, at least 40% of the central dose. So these were very important doses, actually. And you probably didn't, you probably noticed that I never stated yet if they were electron or X-rays. But actually, if you take the 2.8 millijoule curve that I showed before, and you plot the relative dose as a function of distance from the source, and you correct for the inverse square law, so the beam is diverging as a cone, but if you correct from the inverse square law, it's as if you're mimicking a collimated beam that goes straight forward. You get that kind of curve. And this is actually a typical dose profile for low energy electrons. The R values here are just clinical parametric dosimetric parameters, which are not important for today. But this dose profile is really a textbook case of an electron beam. So you can look in the Bible of medical physics called the POD. This is a case for an electron beam. So a dose profile as a function of depth in water for in this case. Electron beams have a certain surface dose. Dose increases with depth, and then it decreases quite drastically. And it ends with a certain Bremsstrahlung tail, so it's X-ray photons that are emitted along the propagation of the electrons. So this dose that is measured incorporates both particles. And we're looking for that Rmax parameter, which is the maximum range of electrons. And this Rmax is above that parameter Rp and somewhere falls near the Bremsstrahlung tail, which is not totally clear where. But in our case, Rp is here at 2.5 meters, and we estimate that Rmax is at most at 6 meters. So we can have that range. And if you convert that into energy, we estimate that we have a maximum electron energy between 0.8 to 1.4 MeV, which is quite substantial already. Yes. Next slide. Again, so if we go in the Bremsstrahlung tail that I just talked about, so in that tail we did an X-ray half value layer measurement. So we got 5 meters from the source where there's only just a photon dose, and we keep adding aluminum slabs in front of the dosimeter to reconstruct the relative dose curve as a function of aluminum thickness, and you get that type of behavior, exponential behavior. And then we can retrieve the half value layers. So this is where the dose drops by a factor of 2. So 50%, 25%, then 12.5%, etc. And using Beer-Lambert law, you can retrieve the attenuation coefficient of the photons. And if you go get the curve on the NICS-XCOM database, you can, the attenuation coefficient is related to a certain energy here. So the effective photon energies that we measured were around 20-25 keV. However, even though the effective energies of the photons is in the tens of keV, photons with energies up to the maximum electron energy of about 1 MeV are expected, because measuring the half value layer is like measuring the average photon spectrum, a parameter that incorporates the entire spectrum of photons. And the spectrum extends up to the maximum electron energy. And photons in the hundreds of keV are much more difficult to shield, actually, as you probably know. Now, regarding the OCLD area dosimeters from Health Canada, this is the official readings from the Health Canada dosimeters after only 100 minutes of acquisition. And actually, they gave us 2 dosimetric parameters. Essentially, this one means the surface dose given by mostly electrons, and this is the body dose mostly given by X-rays. And just to summarize this this table, what we notice from that is that it confirms a highly directional surface dose from the electron, a more isotropic body dose from the X-rays, but most importantly, they reported a dose that is 1,200 times greater than the annual limit. So I don't need to mention that they noted the anomaly, and they wanted us to give us a bit of explanation on this measurement here, which we did with them. Yes. So then we know that high dose emission, that we've measured this high dose emission, we really wondered, like, what's the acceleration process? How can that happen? And we started to investigate a bit what's happening. And since we cannot directly measure the focal spot because the parabola is focusing too tightly, we calculated the focus intensity with an in-house code called the Stratocalculator. So essentially, we have an in-vacuum and ideal beam with no aberrations, and it gives this. This is the intensity of the spot, gives a spot of 1 micron, and a theoretical upper bound on intensity of 1 × 10⁻19 watts per centimeter squared. And this gives an A0 parameter of 4.86. So this is the normalized amplitude of the vector potential. And just a reminder that when A0 is greater than 1, we are in the relativistic intensity regime. So we are well inside that regime now. And if you calculate the cycle average relativistic ponderomotive energy, it is consistent with the measured upper bound on electron energy of 1.4 MeV, as you see with this 1.3 MeV. Now, is it just coincidence? Can it be something else that produces this energy, such as laser wave field acceleration, for instance? This is the most probable one, actually. And so to answer that question, I did a particle in cell, some particle in cell simulation, 2D PIC code with a 2D PIC code. And so here you see the electron and electromagnetic field densities. And what you see there, actually, you see a large electron shock wave, whereas the laser pulse of 1 micron is only contained here. So it cannot, this wide red color here, it's just an electron shock wave that is pushed out by the laser. And you can also look at the electron angular spectrum, so the number of electrons as function of angular divergence and their kinetic energy. And what we notice here is that this is a cone. It forms a conical shape with the maximum energies that are centered mostly on axis, and the lower energies are more and more diverging. And the divergence is of essentially a few tens of degrees. And essentially what we notice from those simulations is that there is no plasma wave. Pixel emission show that it is really a relativistic ponderomotive kick. It reproduces experimental divergence and also the relative energies. Now, this is fine. Let's say we accept that this is what happens. But now, how can this happen really? Like, how can we really reach that that high intensity without clamping in intensity before having too many nonlinear effects in there? And we demonstrated in our work that if you combine a longer wavelength, so here in this case 1.8 micron, and a tight focusing, you get a low B integral and also low accumulation of aberrations on the optics. This leads to a high peak intensity, in this case almost 10⁻19 with only 3 millijoules, and therefore it yields high energies, high electron energies. The second important thing is that we showed that we were able to produce highly ionized air fragments, and this combined with a longer wavelength, it produced a near critical plasma density in air, which is, to me, it's very impressive. People are doing a very fancy setup to produce near critical plasmas, and we we focus really hard with a long wavelength and we get a near critical plasma in ambient air. This is very impressive for me. And that leads to a high conversion efficiency shown by the PIC simulation, and therefore to a high number of electrons. If you want more details, please, I strongly encourage you to go see our work on arXiv. It should soon appear in the next few hours to days. So I'll let you take a print screen if you want of the title, or you can maybe find it back a bit later, or it's going to be online. But I strongly encourage you to go see our work here, which you will find probably very interesting, and I hope will be useful for those who use mid-level class femtosecond laser for their safety, especially. Okay, I'll continue. Now I want to have just a few words about Flash RT. This is an application of having a high dose rate source. The flash effect in radiobiology is associated with a better normal tissue sparing at ultra high dose rate. And it's a mechanism that is still misunderstood. Apparently, it's related to a rapid oxygen depletion in normal tissue. And from that emerged the field of flash radiation therapy, which is now it's a hot topic in medical physics since the first demonstration on mice in 2014, and then on humans in 2019. And so I did a review of all the review papers about Flash RT for that paper for our work. And I don't want to bug you with all those numbers, but what I want you to remember is that our average dose rate was essentially nearly 4 times higher than conventional radiotherapy. So this is actually quite large. And the second thing is that compared to the only other work in literature with a mid-level class laser, or the other work of this kind, which is laser wave field based, actually, the dose per pulse that we measured was slightly lower if you compare it at the same distance and laser pulse energy. But in absolute terms, we were able to reach a higher dose per pulse because we had no vacuum chamber and we were able to measure very close to the source. So this is a very strong advantage of having just have no vacuum chamber, just in air. You can put a sample at 1 millimeter from the source if you'd like, and you would get a massive dose directly. Yeah, and I encourage you to see the discussion about this on arXiv also, which will appear very soon, I hope. Now, I need to give all the credits to François for this magnificent pun here. Of course, probably some of you know that those mid-level lasers are developing at a really fast rate. And just very recently, like 3 weeks ago, in June, the group of Jens Limpert in Jena, they published a paper with a laser that delivers 1.65 millijoules, sub 100 femto, and at 100 kilohertz. So essentially what I'm saying is that you could take all of our dose that you just saw and scale them by a factor of 1,000. And this is what you would get essentially if you focus it tightly. So my message here is that under tight focusing, radiation exposure risk will escalate by several orders of magnitude within a few years. So please be cautious when you use those lasers, and focusing in air for fun is really not recommended in those situations. So my take-home message of today, the first one is that mid-level class femtosecond laser can produce relativistic electrons in ambient air and at high dose rates. And it seems especially true for long wavelengths. And secondly, MeV electron, they travel several meters in air. So this poses a major radiation safety concern for a lab environment, because Bremsstrahlung is therefore produced everywhere in the lab, and these photons can leak out of lab walls. Either it is gypsum walls or concrete walls. So this is really serious. And if it happens to be your case, please consult your local radiation safety officer to implement proper radiation protection procedures. I want to thank also, I would like to thank all the INRS team, the medical physicists from the MUHC, and the funding agencies, of course. And thanks for your attention, and please be careful when focusing in air. Thank you.
Thank you, Simon, for this nice talk. So, questions from the audience? Okay, I see one question from Saeed Kamal.
Hi, thank you very much for this great talk. Some of my research work is in laser micromachining and laser ablation. So your talk has been actually quite eye-opening for me. What I wanted to ask is that the data that you showed primarily was with, I believe, 10 or 20 femtosecond laser and 1.8 micron. And very tight spot size, 1 micron, I believe, was the spot size as you showed. I'm curious to know if you have any sense of how this would be for typical titanium sapphire lasers, which are at 800 nanometer, but also at 120 femtosecond. I assume the pulse duration would be a significant factor here. And I'm wondering if you have any sense of or have done any measurement in that sense.
Yeah, of course. Thanks for your question. It's a really good question. And I can tell you right away that with pulse duration, it's really sensitive. So as soon as you're not completely, not well compressing, you won't get as much dose, especially because it's nonlinear. You saw that here it's a high nonlinear dose scaling. This is an energy, but in intensity, it's a bit the same behavior. So yes, pulse duration is a very strong factor. But then regarding the 800 nanometer, I suspect, we didn't check it yet, and this is what we're going to do very soon, actually this month. We're going to redo that at 800 nanometer. And so we're going to see soon, but my first guess would be that at 800 nanometer, we're going to be a bit farther away from the critical density, and we should get probably the same electron energies, but much less electrons per shot. Not much less, but a bit less. So it should not be as effective, but that would be my first guess. So.
Okay. All right, thank you very much. I look forward to seeing your new results.
Great, thanks a lot.
Thanks.
Emil?
Yeah, I was just going to comment that my background is high energy particle physics. It's really easy to shield X-rays and photons as low energy as 1 million electron volts. You just need a few centimeters of lead, and then maybe surround that with wax to capture some of the bremsstrahlung that is produced. So it is very good. These results are very interesting, but it's really easy to shield.
Mm-hmm. No, of course. Just saying centimeter of lead, it's quite heavy. It necessitates a bit of an infrastructure modification probably, but yes, it's not just like putting a sheet of lead that is very thin, but you're right, yeah, it's not too complicated.
No, and what I could add on this, Emil, is that most labs where people have few millijoule, they don't have lead walls available. That's the important security aspect of this talk. Like people like me who works with few millijoule, we never think of safe. We think of high safety, but not radiation safety.
Yeah, it's the, when you come from the particle physics background, you're used to doing experiments remotely, and that changes things. That changes the equation. Most often in particle physics, you're tens to hundreds of meters away from where your experiment is happening, and there's a completely shielded and locked enclosure. And my guess is that in this research, that's one of the things that people are going to have to move towards. that you actually shield the entire area around your sample, and you can't get into it when you're running the experiment.
Mm-hmm.
The thing is, the lasers, they need a lot of careful adjustments, so we tend to be close to the experiment. Any other questions?
Maybe if I can add to that, there's actually because I also was doing more like I was working more with Joule class lasers before, and we had typically bunkers, just like in high particle physics, to high energy particles to be shielded from the particles we produce. But then in the millijoule class field, I know, like Francois said, I noticed there's not such a thing as radiation shielding. So it's just my message here is just an eye opener about maybe there's a little paradigm shift that we should start to think about radiation safety as much as eye safety in the future with the millijoule class laser. Whereas for Joule class, it's already something that is common to have a massive shielding, of course.
Any other questions, remark? Well, if not, let's thank Simon. And let's join on Gatortown for discussion. Okay, see you later.
Yeah, great. Thanks everybody for being here. And I will keep Zoom open just in case anybody has problems transitioning on the other side. I could make the nasty comment now.